We will now bring in more bodies to the simulation and review how to manage contacts and connections. Note that we'll be starting this module with the upper mount, which will be fully set up with physics conditions and modified with design changes performed in the previous modules. Again, we'll be interested in the mechanical performance of the mounts. Therefore, we will omit the aircraft structure components and will idealize the engine as a lump force. Let's expand the geometry tree and include the forward mount, front mount links, and the aft mount. We'll also include the mount attachment hardware. Recall that you can include or exclude parts from the simulation or from the view with the left two columns. Let's include all these parts in both the simulation and the view. Before beginning the physics setup, we'll need to address a few geometry issues. Typically, you will be able to solve with minimal geometry adjustments in the explore stage. However, it is recommended to address items that could affect the results. Let's start with something that will definitely affect the model. First, let's switch over to the Repair tab in the ribbon. Here, you will have plenty of tools to make any needed geometry repairs. You'll notice that the rear mount is transparent and it is shown to be a surface in the geometry tree. Surfaces cannot be included in the simulations. Therefore, we will need to restore this part back to a solid body. The surface seems to be mostly complete, so it is possibly having a missing face. Select the Missing Faces tool in the Solidify group. Right away, the tool will detect any missing faces, and we can see one is detected in the rear mount. Click the check mark to accept the repair. We can check for any additional fixes in the Fix group. Let's go through a few examples. First, we can click on the Split Edges button and review the edges detected to ensure they are okay to fix. For our case, we are okay to repair, so we'll accept. Next, let's click on the Extra Edges button. You'll notice extra edges on one of the walls. These edges do not serve a purpose, so we'll go ahead and accept the repair. Lastly, we'll click on the Duplicate Faces button. No instances of repair needed are detected. Therefore, we could move on. Note that there are various other tools to repair geometry, including Discovery's powerful Check Geometry tool, which will capture and repair many issues related to corrupt geometry. Let's switch over to the Prepare tab to make a couple of final adjustments. Here, you will have many tools that will help in preparing models for simulation, both in creation and defeaturing aspects. We'll want to use the Remove tools to check a couple of things. First, we'll want to check that we don't have any interferences. Then, we'll want to remove a few rounds that will pose issues as we move forward in our simulation. To check interference, click on the Interference button in the Remove group. We'll be able to see that the upper mount is interfering with the other two mounts. Now, with the Interference tool, we'll be able to remove material from either body to remove that interference. However, we want to preserve the current bodies, so we'll simply move the upper mount. Exit the tool and select the upper mount. Activate the Move tool. Drag the Move origin to the face adjacent to the aft mount to use it as reference. Now, move it up to the upper face of the mount by clicking on the Up To button in the HUD and then on that face. The upper mount is now repositioned and looks okay, but let's verify by clicking on the Interference button. We'll see we do not have an interference anymore. Finally, let's remove some rounds that will be problematic when assigning bolts later in this session. To do so, click on the Rounds button in the Remove group, and we can start selecting multiple rounds by holding Ctrl. Now that the model has been repaired and prepared, we can begin to set up our physics conditions. For this example, we'll assign structural steel to the entire model. Since we have structural steel as our default material, no changes are needed. But recall you can change the material through the Halo or in the Simulation tab. For boundary conditions, we'll keep the structural supports, but we'll want to modify the remote force. We'll want to reassign the remote force attachment points to the corresponding engine attachment points on the forward and aft mounts. First, let's select the attachment holes with the help of the Power Select tool. Let's zoom in to the forward region and let's select the forward holes. Now, pan to the aft region and let's select the aft holes. Now, we can open the Power Select tool by clicking its button on the status bar. Make sure Search All Bodies is on and select all coaxial holes to select the remaining half of the holes. Let's save these faces as a name selection by clicking on this button on the status bar. Let's rename the name selection to Load Faces. Finally, we can use this name selection to update our remote force in the physics tree. Simply right-click on the remote force in the physics tree and select Replace Location. Then click on the Load Faces named selection. Click Escape to exit, and now your remote force is updated. Know that when you use a name selection to assign a geometry selection in the physics tree, the selection auto-updates if you update the name selection, which can be done by right-clicking on the name selection and performing various changes. The last physics update we want to make is to include the newly added bodies to the acceleration load. To do so, right-click on the acceleration load and replace the location. This time, we'll simply drag select all the visible bodies. This completes our physics setup for now, so let's review the physics tree. The physics conditions should all be the same apart from the updates we made. The one thing that will be different than our previous modules will be the addition of bonded contacts. You can click on it to preview the contact regions, and you can select specific contacts by clicking on individual pairs. Additional details and tools are available, but for now, we'll keep all default bonded contacts. Let's now review the fidelity of our model. Recall that the fidelity can be checked with the tools in the Fidelity group of the Simulation tab, and fidelity can be adjusted with the slider under the SID. Note that without adjusting our fidelity and using the same hardware specs, our voxel size is bigger than it was for the single part. That is because as our problem grows in size, more voxels are needed and thus the size increases at a specific fidelity level. Let's slide the fidelity level a bit to the right to get better resolution of the problem. Note the voxel size. Now, at this point, we can proceed to solve. But let's assume that we weren't quite content with the current voxel size because now that we have multiple bodies, we'd like for one to be refined, or perhaps it is much smaller than the other bodies. Let's consider the forward mountlings for example. If we want to refine the voxel size for these bodies, we can just go to the Fidelity group in the Simulation tab and select Local. We will then be able to assign a local fidelity to our bodies of interest. To do so, simply select the two bodies and enter a size smaller than your current global size. Click Accept or hit Enter. Turn on your Size Preview tool to notice that the sizes are different for those two bodies. Now, let's go ahead and solve. Turn off any tools, click on the Solve button, and you will see the results begin to form. You can check if the solution is complete by visually checking that the white progress line is no longer revolving around the SID, or you can hover over the SID and see the status. We can see here that the simulation is marked as complete, and we can start to review our results. We can view the displacement results and the deformed bodies to verify everything is behaving as expected. We'll be able to see the connectivity between multiple bodies, and we can see that we have forward and side motion as expected. There is seemingly large displacements at the forward mountlings, particularly if you have scale deflections on. But note that adjusting to true deformations and reading the legend will show displacements are very small. Let's wrap up this initial assembly simulation by reviewing additional results available. In the legend, we can see contact stress results are now available for post-processing. So now we have an assembly modeled and solved. However, we kept all default options on for connections. So now, let's refine those aspects of the model.